Hello and welcome to the tutorial on recurrent neural network architecture. But to properly understand the characteristics of recurrent neural network architecture, we will go through a simple traditional deep neural network architecture. In the traditional deep neural network architecture, which contains more than one hidden layers, generally takes the input at the same time through input layer which are connected to the hidden layer H1 and then hidden layer H2 and then output layer O, and which generates the output O1 and O2. Now we can observe three important points here. The first important point is we pass all inputs at the same time. The second important part is inputs x1 and x2 are independent to each other. And the third important point is we use different parameters at different layers of the network. Deep neural network has shown a very high success rate in several applications, but it may not be very useful for sequential information. Like if x1 comes and the occurrence of x2 depends upon x1. Similarly, occurrence of x3 has some impact due to the occurrence of x1 and x2 and so on. For such kind of sequential data, we generally use recurrent neural network architecture. The basic idea behind the recurrent neural network architecture is to use the sequential information for deep learning. It is very useful in predicting the next word in a sentence, identifying the meaningful sequence of words, handwriting recognition, speech recognition, machine translation, etc. Or some other applications where data come in sequential fashion. So now let us understand the parameters of a very simple recurrent neural network architecture. Here we have used total 3 hidden layers, 3 layer architecture. Here xt represents the input at time t. xt minus 1 is the previous input and xt plus 1 is the next input with respect to xt. Similarly, st is the hidden state at time t. st minus 1 is the hidden state at time t minus 1 and adjacent to st. st plus 1 is the next hidden state to st. It is important to note that here hidden state generally takes the input from the previous hidden layer output and the weight of neuron connected which connects both hidden layers and then current input. Thus it is able to solve these two problems that we discussed here, that how to handle the impact of other input which occurred earlier in a sequence in predicting the output. Similarly, here OT is the output prediction for the input xt and OT minus 1 is the prediction value, output prediction value for input xt minus 1 and so for OT plus 1. Here V, W and U represents the weight of neurons. For example, W represents the weight of neuron between hidden states. V represents the weight of neuron between hidden state and output state. Different from deep neural network architecture, here It uses same parameters v, w and u across all steps, or we can show that it performs the same task at each step. Now come to a practical question, that how we can use the recurrent neural network to predict something. Suppose we have three words W1, W2 and W3, and PW1 represents the probability of word W1 in the corpus. PW2 given W1 represents the probability of occurrence of word W2 in a sequence having window of size k words when W1 already occurred. Similarly, PW3 is the occurrence of word 3 when W2 and W1 already occurred, and it comes in a sequence, it comes in a window of size k words. But still we are not sure that word W1, W2 and W3 generates a meaningful sequence. To identify the meaningfulness of the sequence, we will pass PW1 value as a first input parameter, this probability value as second input parameter, and third probability value as a third input parameter at time t plus 1. The predicted output value O minus 1 will gives the prediction score for PW1. OT will give the prediction score for word W2, and OT plus 1 will give the prediction score for W3. By using these prediction scores, we can analyze that whether W1, W2 and W3 form the meaningful sequence or not. But it is not so easy, because something which plays very important role here is, other than these probability values, is the weight of these neurons, because these neurons play a very important role in shifting the data from one state to another state. So for accurate prediction, we apply training process, or we train the RNN model. So to train the RNN model, we will take several such kind of training input and identify the optimal weight for these neurons. And after that, when we will pass these values, pass such kind of other values, then we can get the accurate or near to accurate prediction score. So the calculation process used to calculate the prediction score is generally known as forward pass. And the process which correct these values generally known as back propagation. But as here, different from the deep neural network architecture, we takes the input at different time interval, so we take slight different kind of back propagation, which is known as back propagation through time. So we use that back propagation through time based system to update these weights. So this is the general summary and the difference between the recurrent neural network architecture and deep neural network architecture. Now to simplify this architecture, we labeled all these layers. For example, all outputs as output layers, all hidden layer nodes as hidden layer, and all input nodes as input layer. Here W01 is the weight of neuron between hidden layer S0 to S1. W12 is the weight of neuron from S1 to S2, and B0 is the weight of neuron from hidden layer node to output layer node, and similarly V1 and V2. x0 is the input at time interval t0, x1 is the input at time interval t1, x2 is the input at time interval t2. Now we can divide the operations performed by node of hidden layers. Like suppose we take hidden layer node S1. Generally all nodes of these layers performs two different operations. First is the net and second is the out. The net operation actually takes the sum of inputs from all the sources. So here net S1 will take the input from hidden layer output S0 and weight of the neuron W01 associated between them. So S0 into W01 plus current input at time t is equal to 1, which is x1, and weight of the neuron, which is u1. So this is the function of net S1. Now this net S1 will pass to the out function, which generally achieves the non-linearity in the calculated value. To achieve the non-linearity through out functions, a lot of literature suggests to use the 10H, like 10H of net S1 or ReLU function, but for the simplicity we will use the sigmoid function. Actually sigmoid functions can be defined as Sx is equal to 1 plus 1 divided by Sx is equal to 1 divided by 1 plus e to the power minus x, and its value ranges from 0 to 1. The differentiation of Sx, s dash x, or we can represent it as a so this is the simplicity in the differentiation of Sx, and we represent it as sigmoid sign like this. So here we will pass the net S1 through sigmoid functions to generate the output function. So here out S1 will be sigmoid of net S1. Now the out S1 function here, this is the out and this is the net that we calculated. This out will be fed as an input to the output layer node. Again this output layer node performs two different operations. All nodes of the output layer also performs two different operations, and this can be divided as net and out. So net function will take the sum of all input values from all the sources, but here we take only one input, which is actually the output of hidden layer node S1. So in this case our in this case our net O1 will be equal to V1 into out S1. Now to achieve the non-linearity we will pass it to the out function. A lot of literature suggests that at the for the better predictions at output layer we can use the softmax function. Means we can use the softmax of net O1, and this will be equal to the output, it means out O1. But here also we can take the sigmoid functions for simplicity. So in our case, out O1 will be equal to sigmoid of net O1. So here we can fade it like this also. So our out O1 will be equal to 1 divided by 1 plus e to the power minus net O1. And the output of out O1 will be considered as the prediction score for input variable x1. Such type of operation is known as forward pass that we already discussed and simplified from this layer. So in this tutorial we will take some data value, apply the forward pass and check whether the predicted output matches with the given value or not. If doesn't match, then we correct all those weights of the neurons, associated neurons, by using back propagation through time algorithm, and we will repeat this process with multiple given data until we get the optimal value of these neurons. So now let us start with a very simple example. Now suppose we have take a very simple 3-layer recurrent neural network architecture with input value x0, x1 and x2. x0 is equal to 0.2, x1 is 0.3 and x2 is 0.2, and our output is also given. Prediction output for x0 is 0.2, for x1 it is 0.3 and for x2 it is 0.4. And for the simplicity of all operations, we take the weight of all such neurons as 0.5. As the weight of neurons from input layer or to hidden layer generally doesn't play a very significant role in general case, so we initialize all such weight to 1. So to train this recurrent neural network architecture, we start with a forward pass. So now let us start with first layer at time t is equal to 0. Here we will perform two operations with S0. First is the net operations and second is the out operation. So net operation will take the input from x0. As this is the first layer, so we do not have any input from the adjacent hidden layer node. So here net S0 will be equal to U0 into X0. So our U0 is 1 into X0, which is 0.2, which is equal to 0.2. Now we will pass this to the output, which is actually the sigmoid of net functions. So it will be the sigmoid of net functions. So it may be like 1 plus, and we feed this value here, and this will generate this output. So this output will feed to the net part of O0, and here we have neuron with weight V0. So we will multiply the weight of neuron with this output. So it will be equal to net O0 will be equal to V0 into out S0 which is equal to 0.2749. Similarly, the out function will be again the sigmoid of net function. So sigmoid of net S0 calculated by using the same way, and this is the value. Now we'll go through the next layer. In the next layer we have some information from previous layer. So here S1 will again perform two different operations. First is net part and second is out part. So net part of S1 will take the input from the output of the hidden layer associated with the previous input, weight of the neurons between them, weight of the neuron between them, and current input and weight of the neuron with current input layer and hidden layer. So it will be U1 into X1 plus W01 into output of this layer, so out S0. So after using all these values, like X1 value we have 0.3, U1 is already taken as 1, W01 is already given as 0.5 that we already considered, and out S0 we already calculated here. So we will put this value here and we can get this value here. Now we use this value to calculate the out S1. So our out S1 will be the sigmoid of net S1, and this is the final output. Similarly, we will take this output function, output value, and pass as an input to the output layer O1. So again this will perform two different operations, net and out. So the net part will take the input from output of S1 and neuron V1. So it is equal to V1 into out S1. By multiplying the V1 value that we already have and out of S1 that we calculated here, it is equal to 0.3199. Similarly, out of O1 can be calculated by passing this net O1 through sigmoid function. We can get this value, means we will pass this net O1 through like this, we will generate this output. We can repeat the same process to calculate the values at different layers, like net layers, here net S2, and then out layer, out S2, and then again net layer, net O2, and then out O2. Actually our value out O2 will be the prediction score for variable x2. Out O1 that calculated here will be the prediction score for value x1, and out O0 will be the prediction score for variable x0. Now we can see that our given output here is 0.2, but the calculated output is 0.5683. Similarly, the given output is 0.3, but the calculated one is 0.5793. Similarly, here you can also see the difference, 0.4 versus 0.57777. So now we will calculate the error. There are different ways to calculate the error. You can use the entropy to calculate the error also, but here we used the simple squared error functions to calculate the error. Here the total error can be calculated at sum of half into given output minus actual output whole square. So for E2 we can calculate the error as out of given output for O2 and then out of O2 that we calculated here whole square into half, and after the calculation we can get this value. Similarly for E1 we can calculate our given value is here 0.3, our out O1 calculated value is 0.5793. So we can take these two values and calculate the error E1. Similarly we can calculate the error E0. Now we can see that these errors are pretty high, so we can apply the back propagation through time to correct the weight of these neurons, so that we can get the accurate predictions for these variables.